to go into the complexities of designing the software layer underneath, and you want it to be compatible with any software. And so don't worry, not to worry about the software layer, not to worry about how to tackle the hardware challenges and so on. So you run it on the cloud, but that leads to other security challenges. Now you need to trust, you don't want to trust actually this cloud provider now, or you want to minimize the trust on the cloud provider so that the cloud provider does not make money from the nice app that you have developed, or does not manipulate the data or the results which are coming out from this workload. So this is the kind of scenario that we want to minimize the trust on this cloud provider, and to still provide the guarantees back to the relying party. Recall the CEO example. So here is the scenario that and the specific mechanism that I will just describe. For this, let's combine the piece of software, hardware, firmware as one and call it a platform attester. And the whole thing, and this is then the workload attester. And the whole thing which is in this here is as completely an attester. So this is the terminology. So everything inside this is the attester. This is the relying party. And the idea of this mechanism is for the relying party CEO to get confirmation from the cloud that, yes, my workload is running unmodified, the results are reliable, and the software which is running underneath is up to date, has no vulnerabilities, and the hardware running underneath, which is running the software, is actually also up to date, as the latest security patches applied, and so on. So this is the kind of scenario that we have for this specific talk. And there is another entity in between that the relying party or the CEO can take help from, is the verifier, which basically means that I also offload the verification of this workload over to somebody else. And then I trust that verifier to do the verification job correctly. And please note that I will use the verification word. It doesn't mean formal verification. So here, the verifier means simply an entity which is doing the verification that the workload is running correctly, software updates, and so on, everything is applied. So simple verification or verifier will mean this in context, unless I specify formal verification. Right, so this is the kind of scenario. And as I said, let's combine all the entities as an attester, and the entity in between. For this specific talk, I will focus only on the verifier and the attester. And then the relying party will establish some connection with the verifier, let's assume. So what happens at a high level is that we trust a lot of entities now, the hardware, software, firmware, and how do we establish a connection between the verifier and the attester? So this important mechanism is called as attestation. And a very high level idea of this mechanism is that the verifier will send an attestation request to the attester, all the entities combined together. Attester will generate an evidence which will contain its claims, some proofs to show to the verifier that it's running the latest software and the workload is protected, the platform is up to date. And the verifier will then verify that evidence. And then, as a gray here, I have the optional step that it can, after the attestation, it can provision some secrets or sensitive data to the attester once it's sure that the evidence of the workload and the platform are both correct. So this is the scenario, and the problem statement, specifically the three problems that we tackled in this specific work were the TE agnostic attestation architecture, because attestation architecture, one standard exists called RATS, but it's not TE agnostic. So the goal was to have a TE agnostic, and by TE I mean the piece of the software which is actually being protected by the hardware. And once we have this attestation architecture, to provide the mappings of all the TEs to this attestation architecture. So this is very systems engineering related. And the third one is basically the formal specifications, how we mathematically reason about the attestation procedure. And that, I believe, is the most important bit for this specific audience. So this is the part that I will focus on for this specific talk. Right, so we have now a problem statement. We have attestation mechanism in confidential computing, and we want to have some formalization. How do we go about this complex attestation mechanisms? I will now describe a little bit about the approach that we have taken for this specific problem. And the way we decided to go was to have the categories or the groups for attestation, to think about it and to place things accordingly in a place where they belong. We call the first category as the architecture lead solutions, which are at a high level like the specifications. For example, ARM CCA provides the specifications which somebody else can then use to build a solution on top of that. And similarly for RISC-V, on the right side, there are the vendor solutions, by which we mean that the complete products which are usable, that we call as the vendor solutions. So here we have Intel offerings by Intel SGX, which was the previous version. Now Intel has a newer version, which is the VM-based trusted execution environment called TDX. And AMD and IBM similarly have solutions. So the idea here was to categorize them so some verification can actually be, and then provide the templates which can be reused for the verification of others. And so in this category, we have ARM CCA formalization. In this category, the latest solution, Intel TDX. And in this category of frameworks, basically are built on top of these trusted execution environments, providing the guarantees up to the relying party. So in a figure, I had like the verifier and the attester. So on the left was the relying party or the CEO, just recall that example. So back to the, how do we provide this from the verifier back to the relying party? So that's the purpose of frameworks. And here we considered SCOAN. There are other solutions, Grameen, Microsoft Azure, Attestation, and Verizon in this domain. So I will, for this specific talk, be focusing on specifically Intel TDX. And the idea or the approach basically is like this, that, so these are the three blocks I had in the last figure. So we have the TE agnostic attestation architecture-based specifications. I will describe that in a moment. That basically takes care of the three phases of the attestation, which are the provisioning phase, the time the hardware was given that specific secret in terms of, for example, fuses. The initialization part, which means that some steps which are done only once, and the attestation protocol itself, which is the repeatedly done steps whenever the attestation is required. So this forms basically that attestation protocol. And then based on that generic TE agnostic specification, we can do the formal analysis, which I will be talking about specifically in the talk. So what this means is, or what this includes, is basically forming a formal model out of the specifications, and then based on some assumption, proving the required properties, the goals which are required for the protocol to satisfy. And then out of that, get a formal proof of that the formal model under specific assumptions meets the proper meets the requirements under a specified threat model. So this is the core idea. And here, as I said, I will focus more on the specific TDX solution. And the novelty of this work is basically that for this category of CCA and SCOAN, there is no existing formalization before. And so it's the first formalization effort. For TDX, we had a previous work in IEEE Access a couple of years ago, and we have now refined and added a lot of details which have become available in the 2 years. And that includes basically that work actually focused on a specific part, which was this attestation protocol. And in this work, we add the initialization part, as well as the certificate chain, which is included here. and other verifier steps which are used. More specifically, we have now variable measurements as opposed to constant measurements that we had there. Specifically for scone, it was a challenge because it's basically a closed source solution, and it's a solution developed in our group, but the specs were never presented in any of the papers. There are some scientific papers on this, and there are some entities called CAS and LAS. Even this was unclear what exactly do these entities mean. So I would here argue that given unclear specifications and incomplete specifications, it was not really a verification problem. It was rather a design problem to see how the protocols and the system actually works, and to find these via different experiments and so on. And we make some open source contributions for TDX. The artifacts are already available under Apache license, which is quite a generous license. One can reuse and develop their own solutions. And I want to now talk about the first block which we had in the approach, namely the attestation architecture, TE agnostic specifications. There exists the RATS architecture standard, IETF standard 9334, remote attestation procedures. However, there are some limitations of this standard, that it cannot express anonymous attestation as well as local attestation. And Intel TEs actually, there is a mechanism called APID, which Intel uses, which is anonymous attestation. And local attestation is an essential part of remote attestation. And what these guys say is that, okay, so we focus on remote attestation, but local attestation is out of scope of this work. So our argument here is that if this is out of scope, like we cannot really express even the most commonly used Intel TE. So the standard itself is not really helpful unless it can express the actual things which we want to analyze or to verify. So what we did is we submitted the errata for RATS working group, and it has led to at least 2 new drafts. For example, the endorsements and the reference values, the distinction between those. So again, this figure has a lot of details. I will abstract a little bit to present the gist or the main point of this. For that, or specifically, so the 2 problems, the anonymous attestation, for that we add an identity supplier role to the existing standard, which provides the attester with the identity. And for local attestation, there is a simple fix that whenever the standard says evidence, we add a prefix to these terms, local attestation, the local evidence or remote evidence. Local will mean in the context of local attestation, and remote will mean in the context of remote attestation. So this is the core idea of this thing that we added to this. And now with this and clarifying, so the whole draft is written in English. There is no formalization at all. And we clarified via mappings what do endorsement means in terms of Intel TDX, for instance. Intel, what are the reference values for TDX and so on. So just to give you a rough analogy to understand what these terms mean is basically think of this as, let's say, you want to cross a border of a country for which you need a specifically a visa. And imagine this verifier as the border control officer or the visa or the border control officer who is actually interviewing you, for instance. And then this relying party as the government of that country to which you are trying to enter. And the government cannot check each and every person by itself. So what it does, it hires some border control officers after a lot of scrutiny, of course, because if this border control officer makes a wrong decision, then everything is messed up. A wrong person may enter the country, which the government did not want, or a right person might not be allowed to enter the country while he was eligible for entry. So the core idea is that we need to have a lot of scrutiny to verify this verifier itself, which the community has not done a lot of work on. Anyway, now the problem is that the verifier needs to check the verifier or to do the verification of the, the attester. The verifier needs to check the attester. And this is like providing, while crossing the border, for instance, one shows its identity, like this is my passport, and then the visa officer can, the border control officer can actually check by which entity is this this passport issued, for example, and that creates a certificate chain whether this country, the government to which it's trying to enter, trusts that entity, and is this passport forged in some way, is it somehow manipulated or so on. And the reference values provider, think of it as your fingerprints. Sometimes the border control officer also asks you to check, to put your fingerprints and to verify against a reference which you might have provided before, for instance, at the time of the interview, to ensure that the person who is standing in front of the border control officer is exactly the one that that somebody else interviewed that he trusts. And the appraisal policy, think of it as the, so the policy, for instance, after COVID, we all know that there was a requirement of providing a COVID certificate. So these are the things which keep changing. And now it's, for most countries, it's now gone. So policy is defined by the owner, he can have according to its own requirement. And similarly on this side, so the government might have its own policy. Sometimes they might have good relationships with some countries, but they might be changed over the period of time. So there might be some appraisal policies here. So that's about it. And I want to switch gears to the last block, which was the formal analysis, which will be the focus for the rest of the talk. As it might be well known to this audience that there are two main branches, so to say, of the analysis methods. One is symbolic and the other one is computational. Symbolic meaning that we have a perfect cryptography assumption, and then we build or verify the protocols in terms of correctness. And we believe that it is a reasonable level of abstraction to start with for these complex protocols, to start to think, rather than just saying, okay, so these are very complex and having no basis at all. It's at least a starting point to start to think about it. And then maybe in the future, one can have computational proof of the protocols. And we can have at this level unbounded number of sessions using ProVerif and so on, other tools like Tamarind as well. So, however, the limitation of symbolic is that it assumes the cryptographic primitives like hash, MAC, and so on to be perfect. The side channels are out of scope for this, and one can always go to the computational to do a more thorough analysis. And specifically, the tool that we used is ProVerif, and it's based on applied pi calculus. And it's the reason for choosing this in the beginning was when we started this work was that it's faster than a Tamarind prover. It's more it's more automated, and another advantage is that with another tool which is based on similar syntax, it's CryptoVerif, one can extend it to the computational proofs and have in the future also a computational proof out of this. Right. So just to take everyone on board, like formal verification, we verify that the system satisfies some properties, and by system here we mean, in this specific context, a protocol in the presence of the adversary satisfies a specific security property. And this would mean that the system, including this protocol and the adversary, we form an abstract model. The requirements we formalize as properties, and then we verify whether this model satisfies these properties or not. So a bit more zooming into these blocks is a specific approach for based on ProVerif. So for the system model, we have a system configuration, which includes all the entities involved in the protocol, which I will show in a minute. And then the communication between these entities and the computations that each entity does, for example, computing the hash and then the MAC or the signatures and so on, are included in the operational policies. And by combining these two, one can form a symbolic model. On the right side, we had these properties. So we start with security goals that we want to achieve for our protocol. We have security property formalized. We have them formalized as security properties. And now here is the magic of the ProVerif tool itself, that it translates the model and the properties to Horn clauses, try to do the resolution. And if a fact is derivable, it tries to reconstruct the attack at the applied PyCalculus level. And this block actually is exactly what ProVerif is doing. And if the result of this attack reconstruction is yes, it means that we have successfully found an attack corresponding to this specific model for this specific property. If not, so that will mean that the tool is inconclusive. We have to look deeply into the attack trace that was at the Horn clauses level and try to see what exactly was missing that it could not regenerate it at the applied PyCalculus level. And in case the fact is not derivable, so then the property is proved, which means that this specific model that we have created for the protocol satisfies a specific property. So now there are three important things. One is the model, which includes the protocol, and then the adversary, and on this side, what properties are we interested in? So I will go through each of these quickly. Firstly, talking about the properties which are of interest in this context. Again, the same figure, the verifier and the tester, which is the context I had in the beginning. And the properties of interest here are that the integrity of this evidence is maintained, which means that basically this is the tester which was running inside the cloud. And we want to ensure that the cloud provider did not change this evidence which contains the claims, including the identity fields of this attester. So if the cloud provider could change this, it could play the role of that specific workload, show that everything is correct. However, this would not be the case. So we want to have integrity as one of the main goals. And we also want to ensure that the evidence is freshly generated and that it cannot be replayed by the cloud provider. A relevant property to integrity is authentication. The verifier also needs to ensure that the attester, the entity it is talking to is the real attester that it wants to talk to authenticate that specific entity. And then in some specific cases, we need also confidentiality or secrecy. In this, at the symbolic level, it's syntactic secrecy. And the idea here is that the adversary does not see this secret in the plain text. And then we did a lot of sanity checks, breaking the protocol here and there to see that our protocol, that model that we have created is correct and works as expected. So I will now describe a few of these properties. How did we, thinking about how did we formalize it, starting from the intuitive notion that the verifier sends this secret encrypted with the public key of this attester that was generated inside the attester. And basically it wants, so we can think of it as a reachability property, that whether the attacker can get this secret in the plain text or not. So that's basically formalized as a reachability property. And then the integrity of the evidence, as I said, is very important, that whenever a message is accepted, we want to ensure that, so it's basically on this verifier side, whenever a message is accepted from this, the evidence, for instance, generated by this attester, we want to ensure that actually attester was the entity that generated this. And then from formal perspective, this would actually can be formalized as a correspondence assertion, which means that I have some variables of agreement. I define some events in both of the protocol, modules of the protocol for the verifier and the attester. And I put these events message accepted just after when the verifier actually accepted that evidence, and the message sent just before sending this evidence. And then the query is to ensure that whether the attacker is able to get a message accepted without having a message sent by the attester, which would actually mean that the adversary generated this message or adversary could modify this message. So this is basically the thing that we want to verify. That is, with all these variables of agreement, do they remain the same until the message accepted, starting from when the message was sent? And the T1 and Tn here represent in green the types corresponding to these variables. But this query only checks that if a message was accepted at the verifier end. So to remove that if condition, we also need to ensure that at least there was one path in the system where the verifier could accept a message. There is one more problem, that multiple messages at the verifier could be accepted corresponding to a single message sent, for instance, as shown here. And so what we actually need is that one-to-one correspondence between every message accepted and every message sent. So that's basically can be modeled in ProVerif as injective correspondence assertion, just by replacing the event word with the injective. And again, we need to check the reachability of message accepted. Okay, I want to talk now, having seen what kind of properties are of interest, let's switch to the model, how we built that model. The specifications were incomplete, and we argue that, as Barbosa et al. Also described, that we need to integrate formal methods as soon as possible in the design. And that's what we did. Instead of saying that, okay, let's wait for it to complete and have broken designs until then, we want to just start with it. And I will show you next that we were able to shape the design of TDX itself during the process of this formalization. So what we did to fill in the missing details was we had some previous experience with the older technology, SGX, and one specific data center attestation primitives, which the TDX, the newer version, actually reuses. So from our experiments, since TDX is not yet released publicly, so we used the experience or experiments that we did with this in order to understand what could possibly be done in TDX. And we had extensive discussions with Intel, ARM, and S-Contain, the three technologies that I described in the three groups that we had before, Intel TDX, ARM CCA, and SCOAN. And we used these discussions to fill in the gaps. And the TDX specifically, which I used as the running example in this talk, has 6 trusted entities within the protocol. And just to quickly show you about the model itself, it looks like this. There are there is this initialization phase from this to this, and then there is this attestation protocol. The information about provisioning is not yet available, so we haven't modeled that. And coming back to the point on the RATs, that it says that, okay, so leave local attestation apart, we focus on remote attestation. This local attestation forms a big part of the remote attestation. And in fact, which I have not shown here, this part also is actually doing the local attestation between the PCE and the TDQE, which are 2 entities inside this protocol. So this part, as well as this part, until this is actually local attestation going on. And then the remote attestation simply does these signatures and sends over to the verifier via this host VMM, which is untrusted, passing through the guest TD over to the verifier. Right. I want to talk now about the threat model that we have. So as is with the symbolic level, so we have the famous Dolevia model, where the adversary has full control of the communication channel. Measurements, as I said, the hashes corresponding to the pieces of code, we have now variable that the adversary, meaning that the adversary can change these measurements. And the state of the art currently before that uses constant measurements. And we have some technology specific capabilities for the adversary, meaning that, for example, for TDX, adversary has full control to create fake trust domains. Trust domain is the name for the VM for in Intel's terminology. And it can get its evidence, and Intel's terminology for this is the quote. Right. Having seen the approach, I want to describe a few challenges before going to the results. For TDX, which is the one that I'm currently using, so it had like 1,500 pages of specs, and this doesn't mean that I read each and every of page. But somehow many of the things which were interrelated, and we had to go through a lot of these specs in order to find out what exactly does Intel mean when they talk about a specific thing. As you see in the diagram that we have 6 entities, so it's not just a specific attestation protocol itself, but a holistic view of starting from the provisioning up to the attestation protocol. Apart from that, it inherits specification from SGX, and the software development manual alone is of 5,000 pages. Again, it's based on SGX, but not everything is reused. So this is just a rough figure to give the idea of the complexity of the protocol and the specifications. Another problem is that the specifications were given in are still in natural language by Intel, and one can then interpret them in different ways. And not only that, like they are really ambiguous at many points, they are incomplete, and even they are contradicting with what Intel says in another document compared to what they say in another specification documents. And one major issue is that Intel keeps updating the specifications on the same physical website link that they have. And this was really problematic. When a reviewer is actually reviewing this work, he would not find the problems that we are mentioning. So we reported some problems to Intel, and what they do is they update it on the same link, and a reviewer can actually not find out what we describe in the text that, for instance, on this manual page, this and this. So Intel updates on the same link rather than having a different link for the updated specifications. And another way to go about this was, okay, other than specifications, let's look at the code. And when we looked at the code itself and the comments in the code were inconsistent with what Intel said in the specifications. We have several examples here, but for the interest of time, I will go forward that from formal perspective, it was very difficult to have precise model of the adversary, and we try to do our best, and with the model that the adversary can change the measurements, and then the verifier will actually be the one to decide which TD to trust. We wanted to have formal model as realistic as possible, as you see in the big figure that I had shown in the model, to capture all the real details of attestation as closely as possible. And the measurements we took as variable, as I said, and there are a few user-defined inputs, which we try to keep as generic as possible. So when one is reusing the solution, they can actually put in their own specific values in order to test for their own specific use case. So with these challenges, I want to quickly show you some of the results. In the specification documents that Intel had in 2021, when they released specifications for TDX, Intel claimed that this is the set of things that a trust domain or the VM needs to trust, including this Intel TDX module, ACM, TD coding enclave, CPU hardware. The important point here is that Intel claimed basically that all other software is to be considered untrusted by the trust domain. And what we did is we did all the analysis of the specification, and and the code, and doing all the analysis, we found out that this is actually the chain of trust of the entities involved, starting from the Intel's root of trust, the root certificate authority, going up to the virtual machine, which is this trust domain. And the red keys actually show the private parts of the keys corresponding to these entities. And horizontally adjacent, there is a certificate corresponding to each of the entity containing these public keys, and so on up to the final evidence TD quote. And also we show here the certificate revocation lists. So now coming back to the claim of Intel, what we said is that it's not possible to have this specific entity PCE out of the trust domain, because it's within the certificate chain. So something is messed up either with this claim or with this claim. But Intel did not accept our arguments until we could provide them a proof of security, or let's say a breach of security that with ProVerif that, okay, so this is what you claim in the specifications, and now tell us whether this proof is wrong or the model is wrong or actually your claim is wrong. And then Intel had no arguments here, because with the Intel's claim TCB, this is the integrity property, which is for two set of claims, this R data field, which is one of the fields, and TCBI claims. This property is another integrity property for TDI claims, and this is the authentication property. All of them are false, and they are actually, these events are actually reachable. And finally, the confidentiality property is also broken here in case of Intel's claim TCB. And as I said, the artifacts are available here. One can verify independently, and then Intel could accept that, okay, so this TCB is actually broken, and then they changed their specifications to TD attestation software should actually be, all of it, including the PCE, should be trusted by the trust domain. And as I said, what Intel did is that, okay, they updated this, but what they did is that they on the same link, they actually updated these specifications. So one cannot actually now find what happened in 2021, what they had for roughly for 2 years. And one can only find on this link, like the link, what I mean is basically the link for both of these references, 8 and 9 is the, 9 and 10 is basically the same. So what we did is we privately contracted Intel for this, and when it didn't stop, so we also have publicly reported this, which is publicly accessible here. Right, because for us it was a problem that the reviewers cannot really judge what's wrong, and this, if they see the newer version, they don't see what was actually before. So with this, I want to provide a quick summary and outlook of the work. We started here from the attestation analysis 4 years ago, and they have like more than 2,000 reads for DCAP, another scheme, more than 4,000, and community is very interested in this. The people want to understand what exactly goes on behind the scenes, and to understand these complex protocols in some way to design a better system or a better verifier. Similarly, 3,000 plus reads and 2,700 reads. And this is the work that we had made public in January, already 1,800 reads. And this is what we are currently extending, providing the, in this paper, this was only a systemization with a very brief note of the verification. So we are extending this to an extensive formal analysis as a newer version of this paper. So the take home from all this is that basically the attestation designs are designed in an ad hoc way, and confidential computing as a domain itself is still in its infancy, with very little science involved, very little argumentation, scientific argumentation involved. And there's no transparency of the specifications. SCOAN has its specifications on the websites, so one can easily change that without being noticed. And as I said, for Intel, they are on the non-persistent links, and it keeps changing on the same links. There is still a huge gap between the systems engineering community and the formal methods community. System engineering guys want to have some realistic formal models. Formal methods are community is making progress in the formal methods. However, still it's far from what the systems engineering community would like to have been verified. So what we did in this domain is that we have done many initiatives. We have taken many initiatives in this regard. We have added to the curriculum of systems engineering master's program here in TU Dresden some of these things as part of the teaching curriculum for students who have never experienced or learned about formal methods before. It was criticized a lot in the beginning, and I'm not sure what will happen in the future, but we at least we did some initiative that a systems engineer should also be able to think critically about the designs and design the systems in a systematic way. We have a seminar series at TU Dresden where we invite people from formal methods community to present to our systems engineering chair and the OS chair and other relevant chairs in a very high level. If you are interested, you are very welcome to present to us. And we also have another workshop where we have these intersection topics of formal methods and trusted execution environments. So we have TE agnostic infrastructure, but what we are moving towards is basically having the TE agnostic verification infrastructure. So this is what we are aiming at. And in this regard, we have a couple of works in progress. After this Inter-TDX work, Intel contacted us that they want to have verification of the virtual TPM trust domain solution in addition to the trust domain. So there is a user TD and a VTPM TD. How do they both communicate and interact to create a secure channel? So Intel is actually now very interested in this, and we have a big team of this, including people from ARM, Barkhausen Institute, and Intuit, where we are trying to extend the guarantees and have this remote attestation included within the handshake of the TLS protocol. And there is a corresponding draft by the ARM guys here, and this is what we are now formally verifying as well. So the high-level vision of this work is to have open source software, which one can then test and verify. And Verizon is working in this direction. Open source hardware, OCP, is working in this direction. And finally, open source formal verification, where we are contributing towards this. And with this, these are the key references. And with this, I would like to thank you all for this, for attending this, and to welcome you to bring your expertise of formal methods or security to the work that we have, and we would very much welcome any contributions or collaborations if you are interested.
All right. Thank you, Mohammed, very much. So this was an interesting talk, and it has more insights since I last saw it and what's happened with the community at large. And I welcome questions from the audience about the work or in general to Mohammed.
I've got some questions.
Sure.
Did you look at Samson Knox or Google Safety Net at all?
Sorry, say again, Google Safety?
Did you look at Google Safety Net or Samson Knox at all? They're alternative attestation systems.
I see. No, I haven't yet looked about. So is it somehow related to the trusted execution environments, or is it some general attestation framework?
It's a general attestation framework. So I mentioned I've just done a formal analysis of both of those.
Right.
So I've found vulnerabilities against them. So I'd be really interested to compare and see how it works.
Right.
So in that case, there are errors in the attestation framework of Samson Knox v2. And we did our analysis in SAPIC, which is the Proverif syntax, but using the back end of Tamrin.
Right.
And we did that because we wanted to have the time feature to say, is the attestation fresh? So we wanted to avoid an attack where a system is good and attests, and then it's compromised,
right,
and then it replays an old attestation from before it was compromised. So that's kind of time of compromise versus time of attestation.
Right. So this is kind of time of check to time of use kind of.
Exactly.
Right.
Now, would your security properties catch that? Because you've got this injective correspondence, but you could still have a one-to-one. But is that enough? Because isn't what you really want for attestation happened after I requested it?
Right. So basically in the protocol itself, let me go back here. So or maybe I should just a moment. Let me show you a bigger figure of this. Okay. Okay, so basically what we have here related to that is only nonce sent over as a challenge by the verifier. And then the verifier at this end checks that the nonce that it obtained in the evidence is the one that it sent. So just ensuring that the code was, and this code actually then contains this challenge itself as one of the fields.
Cool. So this nonce gives you the freshness. That's good.
Yeah.
And do you model the compromise of the trusted components? Do you allow someone who's trying to attest to start off being honest and then be compromised part of the way through?
Not really. So we assume that all of the entities shown as white in here are actually trusted. Which means that throughout they are trusted and they work as assumed. And the reason is that, as I showed in the snapshots, that if I do not have any of these trusted entities as trusted, so we will have actually the broken attestation. So this was our way of going about, because so for verification, since you have used SEPIC, the very first thing in developing the model is to start, okay, so these are the entities that I want to take in the model. These are the trusted ones. And then the untrusted ones automatically are not required to be modeled. They become a part of the adversary. And then that's the real first step. That's why I really say that in confidential computing attestation protocols specifically, there is not much science that even this assumption since 2021, like the claim of Intel existed with where they claim that, okay, so this is not required to be trusted. That was one of the points. And we made the code very optimizable. For instance, I will quickly show you that just by, we tried to make it as customizable as possible. We took it as trusted, but we also allowed it to be leaked to the adversary just by showing that, for instance, sorry, let me go to that specific place where I show that. It should be in here, right? This one. So just by leaking at the level of symbolic, it would mean that if it is untrusted, it's part of the adversary. But we didn't take as part of the adversary. We modeled all the details that you see, for instance, in the figure here. We modeled all the details of the PCE. But what we did is we just took this step out to see that our formalization actually then preserves all the properties. And then by leaking, with the example that on the slides that I had, it was basically uncommenting this and leaking it out to the adversary, this key of the PCE, and showing that it doesn't work. So basically the goal was to see the TCB of what entities do I actually need to trust. So in short, concluding that we didn't really leak it. Otherwise, if we leak any of these keys, they are really, really important. And this will actually lead to the attacks if any of these entities are compromised.
Cool. Sounds good. It sounds like a fantastic effort you did turning all of that spec into this model. So that's very, very impressive.
Yeah, thank you very much. And I would be very interested in discussing further about later on about your work that seems very relevant. For confidential computing, we do have some separate challenges, but probably we can reuse some of your ideas from that. So I will follow up with you on this.
That'd be great. I'll send you an email.
Sure, great. Thanks a lot.
Thanks.
Are there any questions? Other questions? Okay. Well, I have a question. So
Sure.
at the beginning, obviously, with Intel, you said it wasn't quite clear and so on. And with this new project that has started under the Confidential Computing Consortium or group, is Intel more on board, or what is the situation at the moment?
So Intel is also involved. Sorry, let me go to the slide. So this consortium where the project is being taken up, so CCC Attestation, there are people from Intel itself, like Ned Smith and Dan Middleton. They are part of this whole effort. And in fact, when I mentioned this, that we have made this also done some publicly. So this link is basically a part of the confidential computing. This was addressed to Dan Middleton himself, that we don't see we want to see full transparency of the specs, not that they are updated on the same links. So Intel is very much on board with us, and we have two senior engineers of Intel who are working with us on this solution specifically, which is integration. How do we bootstrap this? And this is probably what Tom also mentioned, that starting from the boot process, the attestation protocol might be able to fool the verifier that the measurements are correct, but how do we ensure that they are really the ones that we want to have? So this is the solution that Intel has for virtual TPM integration within the TD. And how do the two create a secure channel? So this is what we are looking into currently in this follow-up.
Okay, that's very interesting. I have an unrelated question to the consortium, but related to something you said at the beginning, which was that one motivation for using ProVerif was to potentially move to CryptoVerif to do some computational proofs. Is anyone doing computational proofs in CryptoVerif or otherwise as part of this effort at the moment?
You mean for you mean specifically for this our work, or
yes for this work?
So we have a new postdoc in our group who is familiar with EasyCrypt. She has worked with in her PhD with EasyCrypt, but currently we do not have any expertise in CryptoVerif. The initial idea was to sorry, I'm on the wrong slide. This one. So the initial idea was to start at a basic level, because currently the details are not at that level where we believe that computational proofs might be possible. But instead of saying just that, okay, so they are very complex, start reasoning about that. So it might be that she can in the future use these artifacts to move to computational domain, because she has in her PhD done used EasyCrypt. She is familiar with all the computational details. My work is very focused on symbolic throughout.
There might be another way. So EasyCrypt is you said it's not your cup of tea, but it's at the primitive level, and there's something that borrows a lot from the syntax of ProVerif, not from anything to do with PyCalculi, and that's Squirrel. That's a computational prover at the level of protocol, not primitive, as I'm sure you know. But I'd be interested to look at your model and try potentially something like that rather than EasyCrypt. So I might follow up with you on that.
Sure, perfect. So yeah, that would be great.
Okay, so if no one else has any more questions, then I'd like to...
sorry, not a question, but I just wanted to say it must have been so frustrating that Intel were changing their websites without acknowledging it or being public about it.
Right, that's actually true. I mean, imagine yourself as the reviewer. And for example, when you see that, I mean, we spent some efforts of a couple of years for this specific work, and the reviewer says that, I mean, I don't see any problem in that. I see that the TD attestation software is actually is there in the trust domain, and then all of a sudden, like the whole work is gone. And that's really the point that you see here, that August 2021 and February 2023, both of them have exactly the same link.
Yeah, I really have a lot of sympathy with that, with you over that. I think it's awful of Intel. So I think you're taking it very well.
Yeah, thanks.
Okay. If Roberto, you can stop the recording, I will say something. Okay. Now that it's stopped, I don't know you, Tom, but if this work is that you spoke about with Samsung Knox is not published, if you want us to cut the recording before you asked, then I think.
Oh no, it is. It's at HSCCS.
It is, okay. Well, I didn't know whether it was or it wasn't, and you said that you've been working on this, and if it hadn't been, then I was going to suggest that we cut the video.
Thanks, but no, it's fine.
Okay, good. All right. Okay, well, we shall follow up with Mohammed, and Mohammed, thank you once again. And yeah, we'll hear from each other, I think, from me and Nerissa, and probably from people from the UK SPS as well, I think after the summer. So I think in July and August, there will be no talk. Someone correct me if I'm wrong. And the talks will resume in September. Okay.
Cool. Correct.
Thank you all.
Thank you, Anna.
Thank you very much
Bye.
for this.
Mohammed, very much for your talk. It was very interesting.
Thank
Bye.
you.